How do you do, ladies and gentlemen? I'm Julius Sumner Miller, and physics is my business. And my special business today is this subject, the transfer of heat energy by convection. Convection. On an earlier program, I talked about conduction. And here I have taken a piece of clothesline and set it afire, so to say, in a burner, and then shut out the flame, so it is giving me a lot of smoke, abundant smoke, and I've got a real smokestack there, as you see. Now, let's look at this mechanism. Here in this chamber is a candle, a lighted candle, and smoke is coming out of here at a vast rate. Fantastic. I think you can see it. Now I'm going to put some covers on, a cover on that chimney, and the smoke is trying to come out here, but not so well. And if I let this stay for a while, I'm sure the candle would go out. Most assuredly it would go out if I covered both. Now, watch. I'm going to take both off. Do you see? Not quite as well as I'd like it, but I'm going to do it again. Watch it now. Watch it. Watch it. Now I'm going to take this one off, this cover. Watch. I assert that the smoke is falling down. Very little of it is coming up. Very little of it. This is a little different. Oh, there it is. Let me do it again. I'm going to fill this stack now. Watch it. Watch it. Now I'm going to take that cover off. Watch it. Yeah, there it is. There it is. So you saw smoke go down, fall down. This is a wonderful thing. I'm going to pose a little problem for you. Here is a house with a smokestack. I say that on some days I see the smoke come out and go up, 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 up. Then there are other days the smoke comes out, just out of the chimney, and falls down, down, down to the earth. Question, on what kind of day does it do the one, and on what kind of day does it do the other? Well, I'm going to help you a little bit because it's a strange business. It goes up, up, up on a dry day, and it falls down on a damp day. What does this tell us? It tells us that damp air is not as heavy as dry air, and therefore does not provide the buoyant effect necessary to lift the air up, the smoke up. And this is a fantastic thing to say that wet air is lighter than dry air. It has water vapor in it. Wouldn't you think that it would be heavier? But it is not. Now, while that's smoking, here is another. I have a framework, a closed rectangle of glass with some water in it. I am going to put some food coloring in this corner of the framework. Watch it now. Some food coloring. There it is. And you will see it drift down, diffuse down, gravitate down in a wonderful way. Look at it. Look at it. Look at it coming down. It's coming down. It's coming down. Now I'm going to apply some heat to this tube. Watch it now. You see the coloring, which is heavier than water, drifting down and diffusing. Now I'm going to apply some heat energy here. And I say, color, go back. Color, go back. That's what I command it to do. Oh, it's coming down. It's coming down. But I say it should go back. Watch it now. Watch it. Aha! There it's going up. It's going up. And it's going to come down here. So I'm going to play the burner, the flame on this side, and I say, coloring, do not come down. Do not, I say do not. Well, it's coming down. Somebody says, oh, you cannot fight nature, Professor. No, I am not fighting nature. I am collaborating with her, and now it is migrating back. There it is, and I could drive it the other way. So we are talking about convection. Convection, the transfer of heat energy by actual transfer of stuff. Remember, in an earlier program, I talked about conduction, which takes place in solid things like metal rods and wooden rods and the like. Now I am talking about convection, which takes place in fluids, because something must flow, and fluids is the generic name for gases and liquids. So we have this strange business of convection. Another illustration of it, an imaginary experiment. Imagine that I am sitting here smoking a cigarette, which I don't do because I don't smoke. So this is the real part of the experiment. And here I have a reading lamp throwing some light on a physics book. And the lamp is lighted. Question, where does the smoke from my cigarette go? Up here? No, strangely enough, it does not go up here. It goes up under the lamp and out from under the shade. Why? Because the heat of the lamp gives rise to a reduction in the density of the air, and a convection current is set up. Now, regarding this convection, I would remind you, a massive piece of business, because when we have convection on large scale in nature, what do we have? Gales and hurricanes and tornadoes, fantastic energy in the moving air. And yet, consider the moving air. I tried to grab it. As I am led to say, there ain't nothing there. But oh, it is amazing. There are 3 times 10, listen to this, 3 times 10 to the 19 molecules of gas in a cubic centimeter of air. Incredible. An illustration of how big this number is. Supposing you and I and a million other people went to the ocean side and picked up that many grains of sand, and we piled them all up in a pile. How big a pile do you think we'd have? We'd have a pile that is 1 mile wide, 1 mile long, and 1 mile deep, a cubic mile of sand. And as I am given to say further, so you get an idea how big this number is, you know, I'm talking about there ain't nothing in air. 3 times 10 to the 19 grains of sand. Supposing you could count 10 per second. 1, 2, 3, 4, 5, 10. 1, 2, 3, 4, 10. How long do you think it would take to count that many grains of sand? Answer, 100,000 million years. And I say, ain't that something? And there is nothing here to grab. Incredible. More on convection. A beautiful demonstration. I'm going to light a candle here. I'm going to light a candle. And here I'm going to, and it rests in a little saucer, I'm going to put this glass tube on top. And now no air can get in at the bottom, and the candle flame will soon expire. It will asphyxiate for want of air to breathe. Watch it. It's getting light. It's getting dimmer, dimmer, dimmer. Now I'm going to put in a partition. Watch it. Well, I'm having a little... There it is. There it is. It has been revived. It has been revived. Let me take it out, and I assure you the candle flame will go out without this partition. Watch it. Watch it. It's on the verge of going. It's on the verge of going out. On the verge of going out. Yeah, and I'll catch it now and give it a new lease on life. There it is. And what must we say? Well, the physics is clear. I put a partition in this chamber, in this chimney, so that cold air could fall down and the hot air come up. Now, don't ever say that hot air rises, because that ain't so. There ain't no Hindu levitation in this business. What happens is that the less dense air is pushed up by the colder air. Convection. Convection. Oh, a beautiful thing to witness. Have you not seen seagulls, especially seagulls, soaring at certain places in the sky? I once did this in class, and I'm led to tell you, I said to the class, how many see that I'm a bird on the wing? A bird on the wing. And one fellow, not so poetic-minded, said, Professor, you look quite like a vulture. I thought that was terrific. The fellow had an idea, didn't he? Right. All right. So much for convection. Actual transfer of heated stuff as compared with conduction, which is transfer of heat energy alone. Now, on an earlier program, I spoke about conduction and got a little cut off because of time. I want to go back to one of those experiments. Here is a metal hub from which emanates a number of spokes of different materials: brass, copper, iron, aluminum, zinc, nickel, and so on. And here is a wonderful experiment to do. Here's what I do. I take a little steel ball, and with a little bit of soft wax, fix a ball to the end of each rod. A ball to the end of each rod. Now what do? I apply some heat energy from a burner to the hub. The different rods conduct the heat energy at different rates, and obviously the little balls fall off in an inverse order to the conductivity. But an interesting question arises. I have here two identical kinds of rods, an iron rod, an iron rod. They are absolutely alike in their composition, but they differ as follows, and this is a wonderful exercise. They are identically long, but one is skinnier than the other. As a matter of fact, one has that diameter and the other that diameter. This is a diameter D and that's a diameter 2D. And the problem is as follows. Supposing I put a little ball on the end of each, and what do I have? I heat the hub. And in what order do they fall off? Well, I'm going to tell you. Let's look at them, because it's a very difficult problem. This has twice the diameter, therefore it has 4 times the cross-sectional area. 4 times. Therefore it conducts heat away 4 times as fast. But because it is twice the diameter, it has twice the circumference, and therefore it radiates from the surface at twice the rate. So this one does not gain over this one 4 times, but rather only 2 times. So what do? If I put a little ball on the end of this one, no, correction, in the middle of this one, and on the end of that one, they will fall off at the same time. And I hope I've said that correctly, but I got a little fouled up. Indeed, if I said it wrong, then you will write me a letter saying, Professor, what you said was not right. What you said was not right. Notice, I've got a little perspiration in my eye. That is a sort of saline, and it is not pleasant. More on this business of conduction. A wonderful demonstration which you can do. A silver dollar, nice and clean. You put it tightly under a handkerchief, so. Tightly under a handkerchief. There it is, tightly. Now, I wish I had a cigarette. We will imagine that I have a lighted cigarette. This piece of clothes on. Lighted cigarette. I put the lighted end of the cigarette tightly down on the handkerchief, on the coin. Question, what happens? Nothing. Why? Because the clean silver underneath takes the heat energy away, as it did in a certain experiment I did with a wood and metal rod, and the handkerchief is untouched. This is a beautiful little experiment to demonstrate to your kin. Enchanting. Enchanting. Next demonstration. This one you can do. Remember I said what happens first when you put a thermometer into hot water? It shows a diminution in the column. Take a flask like this, fill it with water, put some food coloring in it, fit it with a 1-hole stopper in a glass tube, and the level is right here, more easily seen than the action of a thermometer. Submerge this in a vessel of hot water, and what do you see? Down it goes, for the reason that the glass vessel is heated first and expands. This concludes my recitation, and I thank you for listening.